Google runs thousands of services across millions of machines. They ship to production thousands of times a day. Their search results page has been available to every person on Earth, more or less continuously, for over 2 decades. And their uptime is measured in nines. Not 2 nines, 99%, which sounds impressive until you do the math and realize that's 87 hours of downtime per year. 4 nines, 99.99%. That's 52 minutes of downtime per year. For systems serving billions of users, how do they do this? How does any organization maintain that level of reliability while still shipping constantly? The answer isn't magic. It isn't unlimited budget, although that doesn't hurt. It's a discipline and a set of practices that Google formalized in 2003 and then published for the world in 2016. It's called Site Reliability Engineering, or SRE. Today, I want to take you through the core ideas of SRE, and I want to show you that most of this is applicable to your team, even if you don't have 1,000 engineers and a custom data center. Because the mental models of SRE might be the most valuable things ever published about running production software. I'm Alex. This is Bot Thoughts by AmtocSoft. SRE was invented at Google by a systems engineer named Ben Traynor-Sloss in 2003. The problem was a classic organizational conflict. Product teams wanted to ship fast, operations teams wanted to keep things stable. These goals are genuinely in tension. Every change is a potential reliability incident. Every feature ship is risk. Traditional ops teams managed this tension by saying no, change control processes, lengthy review cycles, approval gates before anything went to production, safety through slowness. Traynor's insight was that this approach doesn't scale. You can't manually review every change in a system that's deploying thousands of times per day. And you can't slow down product development indefinitely. That's a competitive death sentence. SRE's answer: make reliability measurable, then use that measurement to make autonomous decisions about risk. If you can say precisely how reliable a system needs to be, not as reliable as possible, but 99.9% available measured over a rolling 30-day window, then you can quantify how much risk you can take. You can decide systematically when it's safe to ship and when it's not, without a human in the loop for every decision. That measurability is what SRE is built on. And it starts with 2 concepts: SLIs and SLOs. SLI stands for Service Level Indicator. An SLI is a measurement of some aspect of your service's behavior. It's a number that tells you something about how well you're serving users. The most common SLIs are availability, latency, throughput, and error rate. Availability: what percentage of requests are being served successfully, typically measured as successful requests divided by total requests over some time window. Latency: how fast are you serving requests? Usually measured at a percentile. P50 is the median, P95 is the 95th percentile, P99 is the 99th. If your P99 latency is 500 milliseconds, that means 1 in 100 requests takes more than half a second. For latency-sensitive applications, P99 is often more important than the median. Error rate: what fraction of requests are returning errors? 500 errors, timeouts, failed validations, anything that means the user didn't get a successful response. An SLO is a service-level objective. It's a target for your SLI. You take your measurement and you define a threshold. The system should meet this level of performance. For example, availability SLO of 99.9% over a rolling 30 days. P99 latency SLO of 200 milliseconds. Error rate SLO of less than 0.1%. These are internal goals. They're not customer promises. That's what SLAs are for, and SLAs typically have financial penalties for breach. SLOs are your internal engineering targets. They define what good enough looks like, precisely. This precision is everything. When you don't have a defined SLO, is the system reliable enough? Is a philosophical debate. When you have an SLO, it's a factual question. You look at the data. You either met the SLO or you didn't. Here's where SRE gets genuinely clever. If your availability SLO is 99.9% over 30 days, then you have an error budget of 0.1%, the inverse. In terms of time, for a 30-day window, that's about 43 minutes of allowed downtime. That error budget is real. It's how much reliability you can spend on risky things, deployments, experiments, infrastructure changes, before you've violated your SLO. When you have budget, you can ship. When you've burned through your budget, you stop making risky changes until the window rolls forward and you accumulate more budget. This resolves the product versus ops tension elegantly. It's no longer product wanting to go fast versus ops wanting to go slow. It's a shared budget that both teams own. Product teams are incentivized to not burn the error budget carelessly, because when it's gone, their features don't ship. Ops teams are incentivized to not be overly conservative, because an unused error budget is a missed opportunity to iterate. The error budget also changes how you think about incidents. When you have an outage, the question isn't how do we punish whoever caused this. We'll come back to that. The question is how much of our error budget did this consume, and what does that mean for our deployment cadence? An outage that consumed all your error budget for the month means no risky deployments for the rest of the month. That's automatic, policy-driven, not political. The error budget forces a conversation about how reliable your system actually needs to be. Here's a counterintuitive truth from SRE: a system that never fails might be too reliable. If your SLO is 99.9% and your actual availability is 99.99%, you're leaving error budget on the table. You could be shipping more features, running more experiments, taking more risk, and still meeting your SLO. Over-reliability is expensive. Error budgets make that cost visible. Something goes wrong. A service goes down. There's an incident. What happens next? In most engineering organizations, someone gets blamed. Maybe not explicitly, maybe not officially. But there's a culture of finger-pointing, root cause analyses that focus on individual mistakes, and an atmosphere of fear around production changes. Engineers learn to be cautious about shipping because failure has personal consequences. This is counterproductive for at least two reasons. First, in complex systems, failures are almost never the result of a single person's mistake. They're the result of multiple factors aligning badly: design decisions, operational conditions, monitoring gaps, process failures, and yes, sometimes a human error that acted as the trigger. But the trigger is not the cause. Blaming the trigger fixes nothing. Second, if engineers fear blame for failures, they hide problems. They don't surface near misses. They don't write honest postmortems. The organization loses the learning that would prevent the next incident. SRE's answer is the blameless postmortem. After every significant incident, you write a document. The document covers what happened in a factual, timeline-based narrative. The impact: how many users affected, for how long, how much error budget consumed. The root cause analysis: not who did it, but what conditions made this failure possible. And most importantly, the action items. What are we changing about our systems, our processes, our monitoring, our deployment practices to make this class of failure less likely or less severe in the future? The postmortem is about learning and improvement, not accountability and punishment. The premise is, if a reasonable engineer, working with the information they had at the time, made a decision that contributed to an incident, that's a systems problem, not a people problem. The system needs to be changed so that the same information and circumstances don't lead to the same outcome. Blameless postmortems require genuine psychological safety. They require leaders who believe and demonstrate that people who surface problems are valuable, not problems themselves. This is a cultural commitment, not just a process. But the teams that get it right build learning organizations. Every incident makes the system more robust. Every near miss is surfaced and addressed before it becomes a real incident. Here's an idea that sounds absurd until you think about it for a minute. If you want reliable systems, deliberately break them. That's chaos engineering. The practice of intentionally introducing failures into your production or production-like systems to test how they respond. Netflix pioneered this with a tool called Chaos Monkey. Chaos Monkey randomly terminates virtual machine instances in production, not in staging, in production. The premise: if your systems aren't resilient to a single VM failure, you'd rather discover that during a controlled experiment than during a real outage at 3 a.m. This sounds terrifying. And if your systems aren't designed with resilience in mind, it is. That's kind of the point. Modern chaos engineering goes well beyond randomly killing VMs. You can simulate network latency between services. What happens when the database responds 500 milliseconds slower? You can simulate CPU saturation. You can simulate disk failure. You can simulate a third-party API returning 500 errors. You can simulate an entire availability zone going offline. Tools like Chaos Toolkit, Litmus Chaos, Gremlin, and AWS Fault Injection Simulator make this systematic. You define an experiment. You define a steady-state hypothesis. What does normal look like? You run the experiment. You measure whether the system's behavior during the fault matches your hypothesis. If it doesn't, you've found a weakness you didn't know about. Chaos engineering is a confidence-building practice. Over time, as you run experiments and fix the weaknesses you discover, you accumulate evidence that your system is actually resilient, not just theoretically resilient. You stop being surprised by failure modes you didn't anticipate. I want to address the elephant in the room, which is, we don't have 3,000 SREs and 100,000 servers. Does any of this apply to us? Yes, most of it. Here's how. You don't need a dedicated SRE team. One engineer who owns reliability, thinks in SLO terms, and champions postmortems is enough to start. SRE is a mindset before it's a headcount. Define your SLOs. Even if you don't enforce them with hard engineering gates, having written down we aim for 99.5% availability and 200 millisecond P99 latency changes how your team makes decisions. You have something to measure against. Run blameless postmortems for your most significant incidents. Even a simple Google Doc with timeline, impact, root causes, and action items is infinitely better than nothing. The discipline of writing it down surfaces learning that would otherwise be lost. Start instrumenting your services with the SLI metrics that matter. Request success rate and latency are 2 data points. Track them, trend them, alert on them. Know what your actual availability has been over the last 30 days. For chaos engineering, start with the simplest possible experiment, kill an instance of a non-critical service and see what happens. You'll learn something, I promise. The full Google SRE playbook is enormous, and much of it is only relevant at Google's scale. But the core concepts, SLIs, SLOs, error budgets, blameless postmortems, chaos engineering, are universally applicable. They're available for free in the SRE books that Google has published openly. Highly recommended reading. Google's reliability isn't magic. It's measurement, discipline, and a culture that treats failure as a learning opportunity rather than a blame opportunity. SLIs tell you what to measure. SLOs tell you what good looks like. Error budgets make the reliability versus velocity trade-off explicit and automatic. Blameless postmortems turn incidents into organizational learning. Chaos engineering proves your system is actually resilient before it needs to be. You don't need to be Google to use any of this. You need one SLO, one postmortem, and one data point about your actual availability. Start there. The full blog post on SRE fundamentals with concrete templates for SLO documents and postmortem write-ups is in the show notes. This is Bot Thoughts by AmtocSoft. I'm Alex. Subscribe wherever you get your podcasts, and I'll see you in the next episode.